The one signal that changes everything. If a telescope spotted a clear sign of life tomorrow, how would we actually know it was real? And not just a weird planet, a noisy detector, or a glitch quietly fooling us from 40 light years away. In the hunt for alien life, that is the uncomfortable question we almost never ask. We see the headlines all the time. Earth-like planet found, habitable zone world discovered, a new system around a distant star, a rocky planet with the right size, the right orbit, maybe even the right temperature. But while these stories sound like we are on the brink of a cosmic discovery, it should be noted that none of them are confirmations of life. They are hints. They simply tell us a planet might be comfortable for life as we know it. This means we are still stuck at maybe. And maybe is not enough when we are asking whether biology has arisen twice in the universe. Because the real universe is messy. Stars flare. Instruments drift. Chemistry can be surprisingly creative. A strange spectrum in a distant atmosphere. A spike in methane. A curious radio signal that appears once and then vanishes. All of these can be produced by non-living physics. So the core dilemma is not just detecting something odd. It is proving that what we see cannot be explained away by geology, by starlight, or by the quirks of our own data. Why does that bar have to be so high? Because confirming alien life would not just be another discovery about some distant planet. It would rewrite biology by showing that life is not a one-off accident. It would reshape philosophy and religion by forcing us to ask whether we are truly special. It would change how we think about intelligence, about our future, and even about the risks of broadcasting our presence into space. So, it's time to find out the truth about what kind of evidence could carry that weight. A single weird spectrum will not do it. One lonely radio blip will not do it either. Optimistically speaking, there is a signal out there that could change everything. Maybe it is a chemical fingerprint in an exoplanet atmosphere that screams ongoing biology. Maybe it is a precisely tuned radio beacon or a laser pulse that no natural process can mimic. But before anyone can stand up and say, yes, this is it, there's life out there, an enormous amount has to happen behind the scenes. Multiple telescopes must agree. Independent teams must attack the result from every angle and fail to break it. So, let's begin. In this video, we will explore what specific signals scientists are actually hunting for, what instruments we need to see them, and how the scientific community would stress test any claim before the word life is used for real. From habitable headlines to hard proof. So, where are we, really, in the hunt for alien life? We keep seeing headlines about Earth-like planets and new worlds in the Goldilocks zone, but what does that actually tell us about something living there? It should be noted that there are at least 3 very different levels of evidence. At the shallowest level, we simply find a planet in the habitable zone, the right distance from its star for liquid water to be possible on the surface. That is exciting, but it is basically a geometric fact about the orbit, not a biological discovery. TRAPPIST-1, Proxima b, and dozens of others live in this category. TRAPPIST-1 orbits an ultra-cool red dwarf. Proxima b orbits the closest star to the Sun. Both have roughly Earth-like sizes and sit in their star's Goldilocks zone. But while that sounds like a recipe for oceans and maybe even forests, all we truly know is that these worlds receive the right amount of starlight. We do not yet know if they have an atmosphere, if that atmosphere is stable, or if the surface is a frozen desert, a steam bath, or something in between. The second level goes deeper, detecting chemistry that could be linked to life. This means looking at the atmosphere of a planet and asking whether the gases are in a strange imbalance. Oxygen and methane together, for example, are hard to keep around without something constantly replenishing them. If JOEST, or a future telescope, saw that kind of pattern on TRAPPIST-1, it would be far more than a simple habitable zone headline. But even that would not yet be a third level, beyond reasonable doubt confirmation. Volcanoes, stellar activity, or exotic surface chemistry can mimic some biosignatures. A single odd spectrum is not enough. The stakes are enormous. A premature "we found life" press conference that later collapses under better data would damage public trust in science for decades. At the same time, a true positive would be one of the most important discoveries in human history, reshaping how we see our place in the universe. So it's time to find out the truth about what kind of evidence would actually convince us. We have biosignatures, the chemical fingerprints of life in an atmosphere. We have technosignatures, signs of technology such as narrow radio signals, lasers, or artificial pollutants. And around all of that, we have contextual data, the type of star, the age of the system, the kind of planet, its temperature, its radiation environment. Optimistically speaking, no single clue will have to stand alone. We will need a chain of observations from multiple multiple telescopes, all pointing in the same direction. The vague question, "Are we alone?" then becomes much sharper. What specific sequence of measurements would be so strong, so self-consistent, that the global scientific community would finally agree this is life? And if a planet like TRAPPIST-1 ever reaches that threshold, what would that chain actually look like? Step by step, meet the suspects. Biosignatures versus technosignatures. To answer that, we first need to meet the suspects, because in the hunt for alien life, not all clues are created equal. When astronomers stare at a distant planet and ask, "Is something alive there?" they are usually looking for biosignatures. These are patterns in chemistry, light, or structure that are best explained by living processes. Think of an atmosphere with a strange mix of gases that should not peacefully coexist, or a surface with pigments that strongly absorb starlight at specific colors, as if a global layer of alien plants were photosynthesizing. On Earth, the classic example is oxygen and methane. In a stable, dead atmosphere, those two react away fairly quickly. Yet our planet keeps both topped up, because biology is constantly pumping them out. This means a similar chemical imbalance on an exoplanet, especially in the Goldilocks zone, would be a powerful hint that something active is reshaping that atmosphere. But biosignatures can be subtle. A red dwarf star, for instance, bathes its planets in a different spectrum of light, and its flares can break apart molecules in strange ways. Volcanic eruptions, photochemistry driven by harsh ultraviolet light, or even a frozen ocean reflecting starlight can mimic some of the same signals we would expect from life. It should be noted that no exoplanet so far shows a biosignature that everyone agrees on. So, let's begin to add a second suspect: technosignatures. These are not signs of simple microbes, but of technology and industry. A narrowband radio signal coming from a single point in the sky. A precise laser flash repeating in a pattern. Traces of artificial pollutants in a planet's atmosphere that no known geology can produce. Or, in a truly science fiction moment, a grid of city lights glowing on the night side of a distant world. Technosignatures, if we ever found a clear one, would be far more definitive. Physics does not accidentally build radio transmitters, but while biosignatures might be relatively common wherever chemistry and time cooperate, technological civilizations could be rare, brief, or quiet. Optimistically speaking, the universe might be full of living oceans and forests, yet almost silent in radio. Here is the catch. Both categories suffer from false positives and false negatives. A false positive is a dead world that cleverly imitates life. Methane from volcanoes instead of microbes, oxygen from starlight splitting water instead of photosynthesis. A false negative is even more unsettling. What if real alien life exists, but it does not breathe oxygen, does not alter its sky in obvious ways, or never invents technology we can detect? So it's time to find out the truth about our standards of proof. Throughout the rest of this video, we will keep sharpening the core question, not just what could be a sign of life, but what specific patterns would be so strong, so consistent, that we would rewrite the history books for a planet like TRAPPIST-1, the cosmic microscope, telescopes that can see life's fingerprints. To answer that, we need a new kind of microscope, not one you hold in your hand, but one that can dissect the light of a distant planet and pull out the fingerprints of life itself. So, let's begin with the best one we currently have, the James Webb Space Telescope. JWST is not just a pretty picture machine, it is an infrared optimized observatory parked 1.5 million kilometers from Earth, precisely positioned to stare at a star while a planet slips in front of it. As that planet orbits and transits, a tiny fraction of the starlight filters through its atmosphere, if it has one, imprinting chemical signatures onto the light. In the hunt for alien life, this transmission spectroscopy is our first serious tool. By spreading that filtered light into a spectrum, JWST can look for water vapor, carbon dioxide, methane, and other gases that hint at a potentially habitable atmosphere. This is exactly how we have begun to probe worlds around red dwarf stars like TRAPPIST-1, where the planets are small, the star is dim, and the transit signal is just strong enough for us to measure. But while JWST is powerful, it is also selective. It should be noted that its technique works best for close-in planets around small stars, where the planet blocks a larger fraction of the starlight. For a true Earth-like planet around a Sun-like star, the signal is far weaker, the planet is smaller, the star is brighter, and the atmosphere's imprint is almost drowned in light. This means JWST will struggle to see clean, Earth-level biosignatures on the kinds of worlds we most emotionally associate with life. So where do we go from here? On the ground, a new class of giants is rising, like the extremely large telescope in Chile and other 30-40 meter class observatories. Their huge mirrors, combined with advanced adaptive optics that cancel out Earth's turbulent atmosphere, will let us directly image some nearby exoplanets, separating their faint glow from the glare of their host star. For the first time, we will not just watch a transit, visit, we will study the planet's own light. Beyond that, concept missions such as LUVOIR and HABEX take the idea into space, where there is no air to blur the view. These proposed observatories would use coronagraphs or even free-flying star shades to block the star's light, revealing Earth-sized planets in the Goldilocks zone directly. In principle, they could search for detailed biosignatures, oxygen alongside methane, subtle seasonal changes, maybe even signs of hazes produced by life. Optimistically speaking, you can think of all these instruments as stages in a long investigation. JWST and the current fleet tell us which systems are interesting. The ELT-era telescopes will refine the short list, and only the dedicated LifeFinder missions will have the precision to make a truly convincing case that a distant planet is alive. But even if we see those chemical fingerprints, will that really be enough? Or could a lifeless world still fake us out? The two paths to aliens, chemistry or technology. So if a lifeless world can fool us, where should we place our bets? In the hunt for alien life, does the first real confirmation come from a quiet chemical whisper or from a technological shout across the sky? On one path, we have biosignatures. Imagine a distant Earth-like planet in the Goldilocks zone of its star, its surface covered in oceans, forests, maybe only mats of microbes. It never sends a message. It never builds a radio dish. It only breathes. But that breathing reshapes the atmosphere. Oxygen and methane sit together in long-term imbalance. Or we see strange organic molecules that should fall apart unless something keeps replenishing them. The planet itself is silent, but its chemistry is not. On the other path, we have technosignatures. Instead of a quiet, living world, picture a technological civilization that has built transmitters, lasers, perhaps even orbital power stations. From one tiny point in the sky, our radio telescopes pick up a narrowband signal at a single, precise frequency, repeating in a pattern. Or our spectra reveal chlorofluorocarbons, complex industrial pollutants that do not occur naturally in any known atmosphere. This means we would not just be seeing life, we would be seeing technology. So which is more likely to appear first in our data? Many astronomers lean toward biosignatures. Simple life may arise on a huge fraction of habitable planets, especially around common stars like red dwarfs, even if only a few of those worlds ever go on to build machines. Technological civilizations might be rare, short-lived, or simply uninterested in broadcasting. It should be noted that most planets will not be filled with radio telescopes, but they could still be covered in microbes. Yet there is a twist. While biosignatures might be statistically more common, technosignatures could be far more decisive. A strong, repeating radio or laser signal encoding information arriving from a specific orbit in a specific system would be extraordinarily hard to dismiss as natural. The same is true for a pattern of artificial pollutants, or even waste heat from vast energy-collecting structures. Nature is inventive, but it does not usually build transmitters. So it's time to find out the truth about our standards of proof. How unbalanced would an atmosphere have to be before we dare to say, not just potentially habitable, but this planet is alive? And how clear would a technosignature need to look before scientists stand up and say, on the record, this is not just interesting, this is aliens? Optimistically speaking, we might see both paths light up, but which one would finally push us from cautious excitement to a confident yes? Your guide through the Cosmic Evidence Lab. To answer that, we need a guide. And this is where we take the headlines about the universe and unpack what the data actually means. In the hunt for alien life, our job today is to walk you, step by step, through how scientists would really go from a strange signal on a screen to a sober, world-changing announcement that we are not alone. So, let's begin by mapping out where we are headed. First, we need a conceptual toolkit. What actually counts as evidence for life, and why is it so tricky to be sure? We will draw a sharp line between a planet that is merely in the Goldilocks zone and one that shows a true biosignature or technosignature. This means asking, every time we see something exciting, could nature do this without life? Once we have that framework, we will dive deep into biosignatures, the chemical fingerprints of life written into a planet's atmosphere and surface. Oxygen and methane out of balance, complex organics, strange patterns in reflected light. We will see why context matters so much. A red dwarf star, an Earth-like world, and a thick atmosphere can produce very different false positives than a sun-like star and a dry, rocky planet. It should be noted that no exoplanet we know yet has a universally accepted biosignature, and we will explore why. Then, we will switch gears to technosignatures, the potential signs of technology in a distant system. Narrowband radio spikes, laser flashes, possible megastructures, dimming a star, even industrial pollutants, or artificial nightlights on the night side of a world. We will ask which of these would be hardest for nature to fake, and which instruments, from radio arrays to future space telescopes, could actually see them. To keep all of this grounded, we will anchor the abstract ideas in specific case studies. We will revisit the Martian meteorite ALH8401, once hailed as containing fossil microbes, and see how that claim unraveled under scrutiny. We will listen to the famous WOW signal, a radio burst that looked almost too perfect, then faded into mystery. And we will return to modern exoplanet systems like TRAPPIST-1, where planets look temptingly habitable, yet still fall short of a clear yes. So it's time to find out the truth. By the end of this episode, you should be able to look at any future headline about possible alien life and instantly judge how close or how far it really is from confirmation. Before we go on, choose your side. If you had to place a bet right now, what do you think will confirm aliens first? A biosignature in a distant atmosphere or a technosignature in our telescopes? Hold that answer in your mind. We will come back to it once you have seen all the evidence. Why alien life is so hard to prove so if we are holding that bet in our minds. We have to ask something even more uncomfortable. How would we actually know we were right? Because nature is a master of faking us out. In the hunt for alien life, almost every wow signal we imagine has a boring natural twin. Exotic clouds can scatter starlight in ways that mimic hazy, life-filled atmospheres. Volcanic chemistry can pump out methane or sulfur compounds that look biological at first glance. Even simple photochemical reactions driven by a nearby star can build complex molecules that, on a low-resolution plot, might resemble the fingerprints of life. So it's time to find out the truth about why this is so hard. A useful way to think about the problem is in 3 layers. First, there is the environment, the type of star, the size of the planet, how much energy it receives, its temperature, its orbit inside or outside the Goldilocks zone. A small, cool red dwarf bathes its planets in very different light than our sun does, and that changes which gases are stable, which ices form, and how the atmosphere behaves. Second, there is the signal itself. The tiny changes in starlight as a planet passes in front, the smeared out spectrum of its atmosphere, maybe even radio patterns in our telescopes. This is the raw data, the part we can actually measure. But while the signal is what excites us, by itself it is just numbers on a screen. The third layer is the context, and this is where things really live or die. Does the environment plus the signal add up to a physically plausible story? This means we have to ask, could volcanoes, lightning, or weird surface minerals explain these gases? Could stellar flares be sculpting the atmosphere in ways that masquerade as biology? Here, one key idea is disequilibrium. Earth's atmosphere is not in chemical balance. We have abundant oxygen sitting next to methane and organic haze that should be destroyed quickly. Life keeps replenishing them. It should be noted that a strong, sustained chemical imbalance like this is one of the most promising biosignatures we know, but we are trying to see these patterns across tens of light years. For most exoplanets, we do not get continents and clouds, we get a handful of pixels, or a single blurred spectrum. From that, we attempt to reconstruct oceans, weather, geology, maybe even biology. How many different planets could hide behind the same faint line in a spectrum? Optimistically speaking, future telescopes will sharpen this picture, but the lesson remains: no single measurement will ever be enough. True confirmation will come from a web of evidence across environment, signal, and context that keeps surviving every alternative explanation we throw at it. So, if we ever see that web forming around a real planet, what exactly will those clues look like? Life's chemical signature, reading alien atmospheres to answer that. We have to do something strange. We have to read the air of a planet we will never visit, using only its light. In the hunt for alien life, this is where things become almost detective work. When a planet passes in front of its star, a tiny fraction of the starlight filters through its atmosphere. We split that light into a spectrum, a rainbow of colors, and then look for the dark bites missing from it. Each missing color corresponds to a specific gas: oxygen, methane, carbon dioxide, water vapor. It's like holding up a barcode scanner to an entire world. But while that sounds decisive, a single gas rarely tells us the full story. Oxygen, for example, feels like the ultimate sign of life, because plants and microbes on Earth make so much of it. Yet oxygen can also build up if a planet's oceans are blasted apart by ultraviolet light from a star, leaving free oxygen behind. Methane can be belched out by volcanoes or produced in deep, hot rocks. Even complex organic molecules have been found in interstellar space, forming on dust grains without a single cell involved. So it's time to find out the truth. No lone chemical smoking gun will be enough. This means combinations and context matter far more than any individual ingredient. On Earth, we have abundant oxygen living side by side with methane in the same global atmosphere, plus liquid water at the surface, and a relatively stable temperature range in the Goldilocks zone. That mixture is deeply unstable in pure chemistry terms. Oxygen should rapidly destroy methane. The only reason both persist is that life keeps replenishing them. Maintaining that kind of chemical disequilibrium for billions of years with geology alone would be extremely difficult. It should be noted that oxygen, methane, is not the only pairing we are watching. Certain sulfur compounds, like dimethyl sulfide, are produced by ocean life on Earth and could, in principle, imprint a similar signal on an exoplanet. Nitrous oxide, a byproduct of microbial activity here, is another candidate, and if we ever saw clear seasonal changes in gas concentrations, rising and falling in step with the planet's orbit or illumination pattern, that might hint at active biological cycles on the surface or in its oceans. Pattern interrupt for your brain. Imagine JD West or a future telescope watching a distant Earth-like world for years, and the gases in its atmosphere breathe with the seasons. Is that weather, volcanoes, or something more? Optimistically speaking, a truly strong atmospheric biosignature will look like a whole tapestry, not a single thread. We would want a planet in the right temperature range around a relatively calm star with signs of liquid water showing a persistent, globally mixed chemical imbalance that matches what we'd expect from some form of metabolism, and we would demand that every non-biological explanation fail one by one. So, if that is the fingerprint of alien biology, what about the fingerprints of alien technology? When nature pretends to be alive, so, if that is the fingerprint of alien biology, what about the fingerprints of alien technology? Before we rush there, we have to face an uncomfortable truth. Even nature, all by itself, can fake the signs of life. In the hunt for alien life, almost every proposed biosignature has at least one non-biological way to appear. Take oxygen. We instinctively link an oxygen-rich atmosphere to forests, oceans, and something Earth-like breathing. But imagine a planet close to a bright star, where intense ultraviolet light relentlessly breaks apart water molecules. The lightweight hydrogen escapes to space, the heavier oxygen is left behind. And over millions of years, you build up a thick oxygen atmosphere on a completely dead world. To a distant telescope, that planet might look wonderfully habitable. In reality, it is a chemical mirage. This means that context is everything. The same gas around a calm sun-like star and around a hyperactive red dwarf can tell two very different stories. Around some red dwarfs, flares and high-energy radiation are so extreme that they strip atmospheres, shatter molecules, and rebuild them in odd combinations. A planet in the Goldilocks zone of such a system might show oxygen, or even ozone, not because of thriving biology, but because its air has been hammered into that state by its star. From far away, that can look like a false Earth signature. It should be noted that we have already been fooled closer to home. In 1996, a Martian meteorite with the very unromantic name ALH8401 made headlines worldwide. Under the microscope, scientists saw tiny worm-like shapes and intriguing chemical patterns rich in organic carbon. Were these fossil microbes from Mars? For a moment it felt like the answer might be yes. But as more data arrived, alternative explanations piled up. Those structures could form through simple mineral growth. The organics could be produced by inorganic reactions and contamination. Bit by bit, the extraordinary claim crumbled, not because anyone cheated, but because the rock turned out to be a master of imitation. And the universe does this on even grander scales. Telescopes routinely detect complex organic molecules drifting in cold interstellar clouds, far from any planet or star that could host familiar life. Long carbon chains, rings, and alcohols assemble in the dark, stitched together by cosmic rays and dust grains. They are fascinating, but they are not, by themselves, proof of anything living. So, let's begin to see the pattern. Every time we think we have a clear sign, nature offers a chemical trick. The lesson scientists took from past disappointments is harsh, but necessary. Any claim of life must survive a gauntlet of alternative explanations, and the more dramatic the claim, the more brutally it will be tested. Optimistically speaking, if a signal passes that trial, it will be unshakable. But what kind of signal could ever be that strong? Technosignatures. When the universe speaks in code, if chemistry can mislead us, what happens when the universe starts sounding like a coded message? In the hunt for alien life, there is one category of evidence that seems, at least at first glance, almost impossible to fake: technosignatures. These are not just hints of a strange atmosphere or a slightly Earth-like planet. These are signs that something out there is using tools, energy, and information. So, let's begin with the classic image many of us already have: giant radio telescopes, like Arecibo in its prime, or the dishes of the Very Large Array, sweeping the sky and listening for a whisper that does not belong. They search for narrowband, repeating radio signals, tiny spikes at a single frequency that stand out sharply from the broad, messy noise of natural astrophysical sources. Why narrowband? Because nature is usually sloppy, pulsars, masers, and flaring from a red dwarf star all spread their power over ranges of frequencies and drift with time. A truly artificial signal, by contrast, would likely be razor-thin in frequency, extremely stable and structured. This means its intensity might turn on and off in patterns, or it might even carry an encoded message. The way we embed images and commands into our own radio transmissions across the solar system. We already have a haunting example of how close we have come. In 1977, the famous WOW signal appeared as a strong, narrow spike from the direction of Sagittarius. Just for a minute or so, it looked promising. It looked almost perfect, but it never came back. Follow-up observations heard only silence. The lesson is brutal. Without repeatability, without independent telescopes seeing the same thing, a technosignature remains an intriguing ghost, not a discovery. Radio is only the beginning. Technological civilizations might also use powerful lasers for communication. Brief, intense optical flashes, far brighter than any expected from a normal star at a single color of light, could betray a directed beam sweeping past Earth's orbit. Other searches look for strange patterns in starlight itself. If a star dims in a highly irregular, non-periodic way, blocking 20 or 30% of its light with no clear planetary orbit, some have speculated about vast megastructures, like solar collecting swarms, intercepting starlight. There is also the possibility of technosignatures in a planet's atmosphere. It should be noted that certain industrial pollutants, such as chlorofluorocarbons, do not occur naturally in large quantities. A strong spectral fingerprint of such molecules on a distant, otherwise habitable world would be very difficult to explain with volcanoes or geology alone. Optimistically speaking, a confirmed technosignature could be far more decisive than any biosignature. Yet, there is a catch. Technosignatures depend on the existence, longevity, and behavior of technological civilizations, and right now, we have a sample size of exactly one. So it's time to find out the truth. If the universe stays quiet, are we listening in the wrong way, or are we almost alone? The moment of suspicion, a planet that shouldn't exist if the universe stayed quiet on technosignatures, what would it look like when the first truly suspicious planet finally refused to stay quiet? In the hunt for alien life, this is the moment everyone secretly imagines. Picture this, a nearby Earth-sized planet, perhaps only 20 or 30 light-years away, orbiting deep in the Goldilocks zone of a calm, quiet red dwarf star. JOIST and its successors have stared at it for years. Each time the planet crosses the face of its star, a tiny fraction of starlight filters through its atmosphere, and we split that light into a spectrum. The data are clear: abundant oxygen, methane, and water vapor, all present together, all stable over multiple observations. On paper, that is a textbook disequilibrium signature. Oxygen should react away. Methane should be destroyed by starlight. Keeping both in the same atmosphere at the same time over long periods usually requires some active process at the surface. On Earth, that process is life. So it's time to find out the truth. Have we finally caught another living world in the act? Or are we being fooled by a planet that should not exist? Optimistically speaking, the reaction would be explosive. Overnight, that one spectrum would dominate conferences, headlines, and late-night conversations. Teams would rush to reanalyze the raw data, to observe the star-planet system with every instrument available, from JWST to giant ground-based telescopes. People would start whispering the word biosignature, but while the excitement would be real, the skepticism would be immediate. Could stellar activity mimic this pattern? Maybe flares from the red dwarf are sculpting the atmosphere in some exotic way. Could strange geology do it, with massive volcanism releasing methane and some non-biological process splitting water to make oxygen? Could we be staring at an instrumental artifact, a subtle calibration error echoing through the spectrum? It should be noted that every one of those possibilities would be explored in painful detail before anyone dared say life on the record. This means the core question would be carefully rephrased. Are we looking at alien biology, or at the most interesting chemistry experiment in the galaxy? Still one clever natural explanation away from certainty? Even with such a strong candidate, official statements would talk about anomalous or potentially biological signals, about habitability and Earth-like conditions, not about confirmed organisms. And that is where the real story begins, because what happens next is not a single press conference, but years of cross-checks, new instruments, and global scrutiny. The claim either breaks under that pressure or it becomes unbreakable. So, let's begin to unpack what that process would actually look like. Science on trial, how a claim becomes a discovery. So, if a spectrum hints at something Earth-like, what happens in the very first week? Do scientists rush to microphones or shut the door and double-check everything in silence? In the hunt for alien life, the real first step is almost invisible. The discovery team turns inward. They rerun their pipelines, check calibration files, and ask very uncomfortable questions about their own work. Did a hot pixel on the detector fake that methane line? Did a software update mishandle the star's light curve? Could a flare from the red dwarf have slipped through the filters and mimicked an exotic atmosphere? For a while, the goal is not to prove life, but to kill the result if it is fragile. Only when the signal survives that internal stress test does it cautiously step out into the wider scientific world. This means preprints appear online, and quiet but intense talks happen at conferences. Here, specialists in instrumentation, stellar physics, and planetary atmospheres line up to challenge the claim. They ask whether the star's activity cycle was modeled correctly, whether dust in the system could distort the spectrum, whether the retrieval code has hidden assumptions. It should be noted that this phase is deliberately adversarial. If there is a weak link, someone will try to find it, but while arguments on paper are powerful, they are not enough. Independent eyes have to look at the same planet. So other telescopes are called in. Maybe JWST saw the original signal, and then a giant ground-based observatory like the Extremely Large Telescope measures the atmosphere at different wavelengths. Perhaps a future LifeFinder mission targets the same orbit, searching for the same chemical fingerprints with a different technique. If one instrument sees oxygen and methane in disequilibrium, but another sees only noise, that is a warning sign. If they all agree, confidence rises. At the same time, modelers get to work. They build virtual versions of the planet, its star, its geology, and its climate. Could volcanoes, for example, pump out the right mix of gases without any biology at all and keep that balance for millions of years? Could unusual ice chemistry or a strange photochemical cycle in the upper atmosphere mimic a biosignature? Optimistically speaking, the more exotic non-biological explanations you rule out, the more the biological one starts to stand out. So it's time to find out the truth. Only after surviving years of this process does a consensus begin to form. Committees at space agencies and scientific unions then craft carefully worded statements, walking a tightrope between excitement and uncertainty. But what would such an announcement actually say? And how sure could we be that we had not just misunderstood a distant, alien world? System-level reality check. Context is everything to answer that. We have to zoom out. A single strange spectrum from one planet is never enough. In the hunt for alien life, what really matters is whether the entire star system tells a story that makes sense. Astronomers do not treat a planet as an isolated dot. They ask, how old is the star? How violent is it? What other planets share that orbiting neighborhood? And how has the whole system evolved over billions of years? This means any possible biosignature has to fit into a broader, physical narrative, not just a neat-looking chemical spike in the atmosphere. TRAPPIST-1 is a perfect example of this system-level thinking. Here we have a compact family of 7 rocky, Earth-like worlds tightly packed around an ultra-cool red dwarf. Because they all crowd close to the star, many are tidally locked, with one face in eternal day and the other in endless night. We can compare them directly. Which ones kept their atmospheres? Which ones were stripped by flares? And which ones might sit in that delicate Goldilocks zone where liquid water could survive? But while TRAPPIST-1 is unusually calm for a red dwarf, it still flares. Those flares can erode atmospheres and even split water, leaving behind oxygen without any life at all. So if we ever saw oxygen on, say, TRAPPIST-1, we would immediately check the rest of the system. Do the inner planets look scorched and airless? Do the outer ones show signs of severe atmospheric loss? If yes, then that oxygen might just be a scar from stellar violence, not a breath of life. Star type shapes every expectation. Around a quiet, sun-like star with a stable output, a long-lived mixture of oxygen and methane in a planet's atmosphere would be extremely hard to sustain without biology constantly replenishing it. Around a flare-prone red dwarf, the same oxygen-methane hint would trigger more suspicion. It should be noted that some red dwarfs can generate oxygen abiotically through intense ultraviolet radiation and water loss, so context is everything. Here is a pattern interrupt. What if the first clear sign is not chemistry at all, but technology? Imagine a narrowband radio signal, repeating with a precise pattern, coming from a nearby star that we already know hosts at least one habitable zone planet. That would be taken far more seriously than the same blip from a random patch of apparently empty sky. The surrounding planets, their orbits, and their possible atmospheres would all become part of the case file. Optimistically speaking, a robust alien life claim will only survive if the signal and the system context line up. The star's age, its activity, the planet family, and the atmospheric data all have to converge one conclusion: life is not just possible. It is the simplest explanation left standing. So, let's begin to imagine what an announcement like that would actually sound like, line by careful line. So, what would it really take? So what, very concretely, would it actually take for the scientific community to say, yes, this planet hosts alien life? In the hunt for alien life, we can now turn all of this theory into a kind of cosmic checklist. On the biosignature path, imagine a nearby Earth-sized world in the Goldilocks zone of a relatively quiet star, not a wildly flaring red dwarf. We first see a consistent global atmosphere and transit spectra, clear absorption lines from oxygen, water vapor, maybe a hint of methane. Over multiple orbits with different telescopes, that pattern stays stable. This means we are not just catching a random plume or a stellar hiccup, we are watching a whole atmospheric system breathe. Next, the chemistry has to be in long-term disequilibrium. Oxygen and methane coexisting at high levels, for instance, should quickly react away. If dressed, then a future life finder telescope, and later, a giant ground-based observatory like the ELT, all see the same imbalance. At different wavelengths, over years, the case strengthens. We would also model the planet's surface temperature, its orbit, its star's ultraviolet output, asking again and again, can volcanoes, impacts, or exotic geochemistry really do this without life? The techno-signature path looks different, but the logic is similar. Here, the checklist might start with a narrowband, repeating radio signal from a specific star system that we already know hosts planets. The signal locks to that system's motion, it drifts exactly as the planet orbits, and it turns on and off in a pattern that natural plasmas do not produce. Or we might see a sharp spectral line from chlorofluorocarbon, like pollutants, in an otherwise Earth-like atmosphere, persisting decade after decade when no plausible geological source exists. It should be noted that none of this can rest on a single instrument or a single team. Independent groups, using different receivers, different spectrographs, even different analysis pipelines, would have to replicate the result. Optimistically speaking, we would want agreement from radio, optical, and infrared data, all telling the same story, while detailed models systematically eliminate every reasonable, non-biological explanation. Socially, the process would be just as careful. Agencies like NASA and ESA would coordinate embargoed papers, cross-checked by external reviewers, before any dramatic press conference. The language, at least at first, would remain cautious, strong evidence for life, rather than aliens confirmed, even if the graphs look irresistible. So it's time to find out the truth, not in a single headline, but in a slow, methodical consensus. So, given these two paths, which do you think will cross the finish line first? A strange, living atmosphere, or a deliberate technological whisper in the dark? And how will you judge the next big alien life claim you see when our own checklist suddenly seems almost, but not quite, complete? When the universe finally answers back, how will we recognize the reply? We have spent this whole journey trying to turn that abstract question into something we can actually test. We began with that first unsettling problem. If a strange signal or spectrum appears in our data, how do we know it is real, and not just a trick of a distant planet or our own instruments? From there, we walked through biosignatures in an atmosphere, techno-signatures from a civilization, and the long, careful process that turns a late-night suspicion into daytime scientific consensus. In the hunt for alien life, it should be noted that doubt is not a weakness. It is the main tool we use to avoid fooling ourselves. Along the way, we learned to separate two ideas that sound similar, but are completely different. A habitable world is simply a place where liquid water and stable conditions could exist. An inhabited world is one where something has actually taken hold and started to reshape its environment. This means no single measurement, no single gas, no single radio spike will ever be enough. True confirmation will feel less like a drumroll and more like a slow tightening of a net, as independent lines of evidence all pull toward one inescapable conclusion. Right now, telescopes like JET are building the first strands of that net. They are telling us which atmospheres are bare rock, which are steam worlds, which might sit quietly in the Goldilocks zone with the right temperature, but no clear sign of life. The next generation, from giant ground-based observatories to proposed life finder space telescopes, could, within this century, read the faint fingerprints of oxygen, methane, and complex molecules on truly Earth-like planets. Optimistically speaking, some of us alive today may see a spectrum so strange that the only reasonable explanation is biology. But while we wait, what do we do with each exciting headline? So it's time to find out the truth, not just from the title of an article, But from the checklist we have built together, does the claim show a stable, repeating signal? Is there a clear physical process or a techno-signature that fits the data better than noise? Have other teams, other telescopes, other wavelengths seen the same thing? We can all be informed skeptics and enthusiasts at the same time, following missions, reading beyond the first paragraph, and asking what would be needed to rule out the last natural explanation. So, let's begin that part of the story together. If you want to be there when a future telescope finally catches a planet in the act of being alive, stay with us. Subscribe so you do not miss the deep dives into specific systems and missions that might carry the universe's first undeniable hello. Leave a comment with your bet. Will the first confirmation be a living atmosphere, or a deliberate technological whisper in the dark? And when that day comes, we will be here, walking through each piece of evidence, one careful step at a time.